Okay, I think it starts. Okay, so this is the typical conduction problem, right? You know it. If water temperature is higher and T1 greater than T2, you have heat transfer from this direction, from high to low. Okay, what about at the end of this rod, at the end of it, exposed to the environment? Let's say you have a room temperature, T infinite. So between the surface and the room, you have a convection, right? Q conduction. Inside the material is a conduction heat transfer. But between the surface, the ending and the surface to the environment, that's a convection heat transfer, right? Assume T2 on the surface is temperature is higher than T infinite. So the heat will go out like this. Okay. Right? Does that make sense for this problems? Okay, this is very typical, very common problem, right? Heat transfer. Okay, since you're exposed to the air, you have convection. But my question is this: what is the relationship between the conduction in this problem and the convection in this problem? Which one's bigger?
They are the same.
They are the same? You sure?
Only so much. Well, it depends if you have radiation.
Okay, let's say there's no radiation here yet. Okay. Hold on, let me omit a couple of people. Okay, does everybody agree with what he said? Who answered it? I didn't see the face.
This was me.
Oh, okay, Jake. Okay. Does everybody agree the conduction equals to the convection heat transfer rate? You are the jury. Is he guilty or not? Is that right? And why?
Well, the convection can only take so much heat that like the conduction can bring to T2. So T1 is transferring heat or to T2, and the convection can only take so much heat off as T1 conducts. Like through the pipe.
Okay.
That's what I think, at least.
What you said is the heat will be just totally transferred into the air in the environment. Right? I guess so. I agree. And if you look at the energy point of view, okay, so where does the energy go if it's not equal? You see, I don't know if it's energy balance. You look at I don't know if previous teacher talked about this. If you have a element, let's say it's a 1D, energy go in from here, energy go out from here. Okay, so then what? This is the volume, right? Then you have what? Energy generation. E dot, let's say it's insulated in this the top and bottom. So it's, let's say, simplify it, 1D energy transfer. Okay, so energy in, energy out. Okay, so the energy out will be equals to the energy in plus or minus, right? Heat generation. Is that right? Heat generation. Let's use a little case, lowercase e, per volume times the total volume. Energy generation has to be related to the volume, right? Okay, so that's a general form. So you include everything. So even include the energy production inside the volume as well as the energy reduction, right? Source and the sink. Okay, if it's a sink, then it's negative sign here, right? Energy taken away or energy generated inside. Okay, so that's the general. It should work on every situation, right? But now Now you know everything about the conduction in the left side of the surface. You see, think about you have a surface here. Okay, anything on the left side is conduction. Energy in is Q conduction. Right? Energy out is Q convection. We're just look at the the interface. Okay, the interface. So if you are the interface, you see, hey, I have energy coming in from the conduction. Okay, I have energy goes out through me to the environment. Okay, but where is the energy generation term goes? Well, doesn't matter. Even you have this is the source. Even this thing generates the heat, generate heat from what, nuclear reaction, whatever. Okay, but the problem is the energy generation is the energy generation rate times the volume. If your target is the interface, what is the volume of the interface? What is the volume? Educated guess.
0, because it's an area.
It's 0. That's no volume. If you just want to see a energy transfer through a interface, through a surface, then whatever the material is, or air, whatever the material of air is, it doesn't matter. Whatever that generation in the conduction in the material or not. But on that cross section, on that surface, there's no volume. If there's no volume, there's no energy generation. Okay, when you go through that surface, energy in has to be equal to energy out. Okay, does that make sense? Okay, this is from, so it's easy for you to just remember, okay, cross a surface, the energy has to be equal in and out, okay? In that sense, because of this, we can go back to this equation, Q conduction equals the Q convection. Okay, equals the Q convection. So that's the fundamental, that's a principle. If you have a multi-mode heat transfers, okay? You probably want to identify that cross-section, the interface between the different modes, between the conduction, convection, radiation, okay? Then you can first write down that equation, the energy balance. Through that surface, in and out, they have to equal to the same. But what if there's radiation going out also? Q radiation, although you don't know the equation yet, right? But doesn't matter, there's a heat transfer, okay? Is that there could be a value of radiation. Then in that cross section, what is the in? Okay, heat transfer in is just the conduction. All right. Then what is the out? Energy form. Out, now you have Q radiation maybe. Okay, but if there's no radiation, it's just conduction equal to convection. Okay. Right? So that's the missing link between the two separate topics we conveyed in the previous couple of weeks. Okay, that's a missing link. So some of you already try the homework problem 1.7. Well, that's really good because we haven't talked about this yet. That's why you have trouble doing it. Okay, you cannot bridge the conduction and the convection for that problem. Okay, now I guess it's a little bit easier to do, right, for 1.7. Now you know. Okay. You can jump in anytime, okay? So if you have questions, let me know. So let's look at the problem, example 1.3, okay? Let's see. let me get a new page. Example 1.3, okay. Okay, so it said, assuming the plate in example 1.2 is made of carbon steel. Do you remember 1.2? I did it last time, right? I can draw. Last time we have a convection, right? The plate has the area of what, 50, it's the convection. The air goes over the plate, right? It's 50 by 75 centimeter in dimension. But in 1.2 at that time, yesterday, Monday when we talk about it, there's no thickness of the plate, right? There's only the surface area, right? The temperature on the surface is what, 250? Temperature of the air is 20 degrees Celsius. 20 on the surface is 250 degrees Celsius. Okay. The convection heat transfer coefficient H is given 25 watt per meter square. Okay. Now in the problem 1.3, it says, hey, in this is the thickness here. The thickness is 2 centimeter for the thickness of the plate. And it is, what's the material of that? Carbon steel, 1% carbon steel. And you have a K, okay? I think the K should be given. The K of the carbon steel is, let me see, what is the K? K is 40, 43 watt per meter square K, right? Okay, so now it says that's also radiation, not only convection. Q convection and also Q radiation. Okay, the radiation heat transfer rate from the surface, well, it's a hot surface, right? The ambient temperature is lower, so you have a radiation going out of the surface, okay? The radiation heat transfer rate is 300 watt. 300 watt of heat is lost through the surface by radiation. K, I think, is not 30, 40, 43. It is. Okay, 43 watt per meter square K. So in this problem, the heat transfer from the surface to the ambient has convection and the radiation. But inside the material, it thinks that the thickness, right? And it has conduction inside the plate. Okay, so it asks you to calculate the inside the plate temperature. Okay, so the heat conduction through the plate must be equal to the sum of the convection and the radiation. Okay, so this problem started from this. So we want to calculate, let's say, temperature on the end of the wall. Let's say T1. Okay. Okay. On the other side of the wall, surface temperature is 250 degrees Celsius, right? That's given from problem 1.2. Okay. Now, you know, T1 on the other side of the plate. Should the T1 greater than 250 or less than 250? Is it hotter on the other side of the plate?
I assume.
It should be hotter because look at the direction of the heat flow. Heat transfer is going out of the surface to the ambient, okay? So for the top surface, there must be an inlet heat transfer. There's a heat going into that top surface of the plate, okay? One side of the surface heat going out, the other side has to be going in. So the direction of the conduction must go this way, conduction inside the plate. Does that make sense? If the conduction is this direction, the other end, the other side of the surface has to be higher temperature, has to be hotter. Then the heat transfer conduction from hot to cooler. Okay, so T1 here on the other side of the plate should be greater, has temperature greater than 250. Okay. That's for sure. After you do the calculation, it turns out to be 235 on T1. Then you must made some mistake, right? You can easily check that like that. Okay. So for this problem, easy, right? So just like I said, you identify the interface for the multi-mode heat transfer. So that interface is your top surface, obviously, for this problem. Okay, top surface. So write down the energy balance on the interface on the top surface. So it will be Q conduction. Oh, what did I do? Can I undo it? Eraser. Okay, good. Okay, so the energy balance will be on the top surface of the plate will be, oh, I have to select the writing pen, right? Will be Q conduction equals Q convection plus Q radiation. Okay, so that's your fundamental, the basic equation for this problem. If this problem is a quiz problem, I'm looking for this equation basically. Okay, strictly speaking, if you can write a couple sentences, couple words on top of the equation, that's the energy balance. Top surface. That would be great. Okay, if you write down this on your test paper, then I know what are you looking at and what your equation is about. Okay. Okay, this problem is simple, so it's pretty obvious. Okay, some problem you see in the homework, you know, it could be more complicated. Okay. Okay, so what do we know now? Anything we know? I think the Q convection has been calculated from example 1.2, the previous example. The total heat transfer, convection heat transfer rate going out based on the surface temperature and the ambient temperature and the heat transfer coefficient is calculated 2156 watt. 2156 watt. Okay. So what else we know? Is radiation heat transfer rate is given? I think it's given. It doesn't ask you to do the calculation for radiation part. It just say it's a rate is 300 watt. Okay. Okay, that's how I solve a problem. I write down the equation. Let's see all those letters I use in the equation. Do I have the values? Okay, if I have value, I write it down. If I don't have the value, I try to write an expression for that letter. Okay, very important. Okay, that's the procedure for you to solve problem. Conduction. Now, look at the inside of the plate, conduction. Do we know the value? I know it's 2456. I know the total value, but it doesn't help. It asks us to calculate the temperature T1, right, on the other end of the surface. Okay, so I need to write down the expression for the conduction heat transfer. Okay, so conduction heat transfer. What is the expression?
Negative K A
Negative, yes.
dt dx.
Negative K A. Okay. Can I use delta T over delta X? Okay, first of all, I have to define the X dimension. I hate to just using an arbitrary delta X here without drawing it on my diagram. What is your X direction? Okay, usually X direction is horizontal, but for this problem, it's vertical. It's a 1D problem, right? So, but define it, okay? As an engineer, you guys, when you go to work, you do some calculation, write on your paper, that's your record, okay? That's your record. People come back to sue you if there's something wrong with it, okay? So write it clearly, okay? Be a very organized and write on paper very neat, okay? So X dimension, right? Can I do this, delta T over delta X? Last time we talked about it, remember? If it's a linear inside, if there's no heat generation inside, we can simply use this, right? If your area, if your cross-sectional area, if your area the heat flow pass, if that area doesn't change also, right? If the temperature is linear, temperature change linearly inside the material, then we can just simply, don't have to use dt over dx, right? We don't need to solve a derivative, okay? It's just delta T. The temperature difference between top and bottom surface divided by the thickness of the plate, okay? So, okay, I write down this. Do I have my unknown in the equation? If I do, I'm good, I'm happy. Then they're just piece of cake to solve it, right? Is my unknown in it? My unknown is what? The goal is to calculate T1, right? Okay, is T1 in there? Yeah, it looks like a delta T, right? T1 should be in the delta T, okay? So let's write one more line and putting the values of K. Negative K is 43, right? Watt per meter square K. I always like to keep the unit, okay? It's for yourself to check to see if everything's right. Unit has to be consistent from left to the right, okay? What is A, do you know? What's A here?
0.75 times 0.5.
Yeah, that's the surface area, right? The area doesn't change along the heat flow direction, okay? So it's a constant. It's much easier to solve if it's a constant area. See, 1.7, the reason it's difficult, homework 1.7. It's a cylinder. You go through, heat goes through the cylinder wall, right? So the area, the cross-section, not cross-section, the area that heat flow goes through, it's not constant. Remember, how do we calculate the heat transfer rate in conduction? With the cylindrical coordinates, the area is not constant. We have an example problem, right? If you have the notes, okay? So you have to go through that way to calculate the heat conduction heat transfer rate. Then equal to the convection, okay? So 1.7 is not very straightforward. You have to go through different steps. Okay, here, area is easy, 0.75 times 0.5 meter square, okay? Not a problem. Okay, delta T, delta X. What is delta X? That's easier, all right? 0.02 meter. Okay, strictly follow the procedure here. You put the unit there, avoiding you to make a mistake, preventing you from making mistake. You see 2 centimeter down there, it's easier to just put 2 down here. Okay, they will be totally wrong there. Okay, it's 0.02, you have to convert it into meter. Delta T, it will be T surface minus T1. Be careful with the order. Downstream temperature minus upstream temperature. Okay, downstream minus upstream. Because there's a negative sign here. Be careful. The equation has a negative sign. You have to follow the rule. So downstream minus upstream. Don't give me T1 minus 250. Then you will have an opposite negative temperature. Right hand side, you can just calculate it, 2456 watt. Okay? Is that good? Everybody follow me? Okay, so now it's a piece of cake, right? This is really happy. I'm happy to see this. Only one unknown, which is my goal, okay? So you can easily solve it. If this problem is 20 points, if you stop here, I say, hey, bye-bye, Dr. Zhang, I don't want to continue to calculate this T1. This is what I wrote on my paper. You get 18 out of 20. Okay, serious, I don't care. If you, every problem, in my test, every problem you got 18 out of 20, you're super good. I told the other guy in my fluids class too. Okay, so I don't care. This is the calculation, just keying the calculator. As long as you put all the units right, everything here, you got it. Okay, so the temperature will be T1. If you calculate it, it will be 253.05 Celsius. Okay, so when you look at your result, always examine it. Take a look, check, double check, see if it's reasonable. It has to be higher than 250. Is it higher? Yes, it does. Okay, it is higher, so it's good. If it's higher, I mean it's reasonable at least. It's not too bad. Okay, maybe you made some mistake in the calculation. Hey, anyway, it doesn't matter. 18 out of 20, I'm happy. Okay. But write down the equation. This is a good example to show you how to show me the process of solving a problem. Okay, it's really, really more important than the correct answer. To me, the correct answer may be 2 out of 20. Okay. But the steps and the units, the values you substitute, okay, you're putting there, that's more than important. Okay, so this is example 1.3. Okay, let me also give you example 1.4. I think that's a good problem. Example 1.4. Hey guys, any question, just jump in, okay? I just want you to fully learn it during the class time. I don't want to waste any second here, okay? Fully understand, then can save you time after class, okay? I know everybody's busy, especially this semester, okay? What does 1.4 says? An electric current is passed through a wire 1 millimeter in diameter. Okay, and 10 centimeter long. Diameter is very tiny, 1 millimeter. Okay, the wire is submerged in liquid water at atmospheric pressure, and the current is increased until the water boils. For the situation, so water is in the surrounding, okay? So you have a convection heat transfer goes to the water. The convection coefficient is 5,000 watt per meter square, C, okay? And the water temperature will be 100 degrees. You boil it, right? Tea water. Well, this is a very practical application. You usually, you heat a wire and then the wire to heat the water, okay? How much electric power must be supplied to the wire to maintain the surface temperature at 114? Okay, I give you a surface temperature, though this problem is easy. Okay, you want to maintain, you want to give the electrical power, right? To maintain, it's a heater, right? It's to maintain the surface temperature of the wire to 114 degree. So you can heat the water in the surrounding to 100 degrees Celsius. Okay, how much power? Let me change that question a little bit. What is the current needed? What is the letter for current? I, right? Assume the voltage is, what is the voltage here in this country? 110, right? Is that right? What is the current needed? You have to distribute give power, right? You need to give a current, amp. How many amp needed to maintain the surface temperature 114 to heat the water into 100? Okay, so how do we do?
We write down our convection equation.
Yeah, that's just convection equation because this one there's no conduction in there, right? So the convection, but you have to know what is Q, right? Okay, just memorize this equation, okay? And then also memorize the conduction equation. There's a negative sign for the conduction, but for the convection is no negative, okay? But the temperature is surface minus ambient, okay? Okay, so this is our convection, good. That's the first step, okay? To see, then after you write down the equation, right? You ask yourself, do I know all the letters? And does my unknown in the equation? Two questions, right? I start from the easy one. So let me find out everything I know and put it in the equation. Substitute that value into the equation, right? Okay. Whatever, what do I know? I know the H, obviously. Okay, I know H, good. Do I know area? What is the area we are talking about in this problem? Surface area, right? The heating surface area, okay? The effective heating area, okay? So it's the outside the surface area of that wire. Do you know how to calculate the surface area of a wire?
I assume it'd be the circumference times the length.
That's right. Be careful. It's not the cross-sectional area times the length, okay? To calculate the surface area of a cylinder, many students will make a mistake by doing pi r square times the h, the length. That's wrong. That's the volume, actually. Okay, you're calculating the surface area of this wire, okay? So the equation will be pi d. D, what is a d? 1 millimeter, okay? Point d, 0.001 meter, right? Pi d times the length, 0.1 meter, okay? then times, is that right? Everybody follow me? The area, surface area. Okay, in solving some of those engineering problems, you really need to know the geometry, okay? Okay, this is the basic geometries. Pi d times the length, the circumference times the length, okay? If you don't know this before this class, it's all right, but now you need to memorize it if you don't know. Okay, then Ts minus Tw, do we know the temperatures? Yes, we do. 114 Celsius minus 100 Celsius. Okay, that's good. So we can calculate the Q. Okay, that's easy. Actually, that was the problem. What is the energy, electrical power supplied? So basically, the problem just tests you to see if you understand the electrical power needed is just equivalent to the heat transfer. It's 100% convert from the electrical power into the heat, basically, for this problem. Okay, that's the concept. But now I changed the problem a little bit. I say, hey, what is the amp current you needed for for this problem? Given voltage 110 volt. So this Q is electrical power. Is the heat transfer rate going out is equivalent to the electrical power supplied to the wire, right? So the electrical power will be equals to voltage times the current. Okay, voltage times the current. Hey, this is a very practical problem, right? Now you know something useful. Okay, electrical power. Electrical heater basically is this principle. Electrical heater. If you have an electrical heater, the water boil. Sometimes those heater can boil water. You can take a look of the in the back of the specs, the voltage, current, power, everything's there. Then you know what is the heat transfer rate goes to the water. Then you can calculate how long it takes the water to boil, basically. Okay, from the later chapter, you should be able to calculate. Okay, so the current equal, oh, okay, now I don't have the answer. Okay, current times 110 volt equals, what is the Q? 21.99 watt. That's a reasonable heater. 22 watt. It's about 75 BTU per hour. Okay, so the current, it's just a tiny little bit current. You don't need much, divided by 100.2, maybe, approximately. I don't have a calculator with me now. Amp. What is amp you use? AMP? Okay. Okay, so this is another problem for the heat balance, convection heat transfer. Okay. Any question? Is that good? So for the homework 1.7, okay, 1.7. I don't want to give you the answer, but I will talk about it here. Okay. You don't have much homework, so practice all of them. Maybe that will be one of the quiz problems in the future. I don't want to give you a quiz this week. Seems like some of you still couldn't attend. Okay, but start from next week, I will start to give some quiz. Okay, be prepared. So 1.7, what does it say? 50 centimeter diameter pipeline in the Arctic carry hot oils 30 degrees Celsius, right? 0.7. Also similar to this problem, okay? So hot oil, temperature is 30 Celsius. Oh, somebody is waiting in the wait room. Surrounding temperature, T infinite, negative 20 degrees C, cold place. A special powder insulation, 5 centimeter, So if you draw it from a, let's exaggerate it for the pipe. This is the pipe. So this is the insulation portion. Okay, as the powder insulation, 5 centimeter thick. Okay, surrounds the pipe. And the thermal conductivity, so you have a K for the insulation is 7. It's very little, right? 7 milliwatt to 10 to the negative 3 watt per meter C. Okay, so the K has to be small. If you any insulation, right? If the K is too big, you probably don't want to use it as the insulation, right? The insulation for the K, the thermal conductivity has to be tiny, so it will stop the heat. Okay, insulate. Okay, the convection heat transfer coefficient on the outside. So outside, H T outside is what, negative 20, right? T inside is 30 degree, and the H is 9 watt per meter square C. Okay. Estimate the energy loss from the pipe per meter length. So that's the energy Q1, Q in, Q out. What is the loss of energy, delta Q? The pipe is going this, right? So first of all, delta Q in this drawing, Q1 minus Q0 is equivalent to what? That's the key. This is the internal heat transfer problem, right? Last class, we talked about the internal heat transfer. The energy loss, change of energy along the flow direction, equivalent to the energy goes to that direction. Okay, I'm out of letters, so let's say the Q going out. Can I just say Q conduction here? Okay, from the oil, 30 degrees Celsius hot oil, the heat transfer goes out. It goes through the insulation part first, right? That's a conduction first. It doesn't directly in contact with air. Okay, so the total energy change from the inlet to the outlet will be equivalent to the total energy heat transfer go from the hot oil to the insulation. So equal to the Q conduction. Nowhere else to go, right? It's not directly in contact with air. So there's no directly convection yet from the oil to the air. You have a separation, you have a conduction here. Is that right? Okay, so basically this problem is just to ask you, what is the Q conduction in the insulation part? Okay, but this problem has there's a lack of information. It seems like you have for this insulation part. Okay, remember this is exactly the example I gave you for the cylindrical coordinate, for the how to calculate the conduction for the cylindrical coordinate. Right? Look at the notes before. They're exactly the same problem. Cylindrical coordinate, the conduction in the ring. Okay. So basically that's our goal. But there's one difference between that example and here. In that example, you have the inner circle temperature as well as the temperature on the outer circle in that previous example. So we can go through it, no problem, calculate the conduction heat transfer rate, okay? But in this problem, you have the temperature on the inner circle, which is 30 degrees. which is the oil temperature. But do you have the temperature on the outer circle? Hey, come on, it's not given. It gives you instead the temperature on the air, -20. But that gives you one additional unknown, right? One uncertain. What is the surface temperature? If I know the surface temperature, outer circle surface temperature, then I can calculate, just like in the example. But without that, but we have additional conditions. Then from the outer surface to the air, you have a Q convection. Instead, we have one additional equation, Q conduction equals to Q convection. Okay, that's additional information. Although we don't have the outer surface temperature, but we have an additional equation you can utilize. One more equation you can solve for, one more unknown, right? Okay, I would stop here. I think now you should be able to handle this with these two equations. Okay, does that make sense? Okay, try it. I really like it. I don't want to give you too many homework problems. Okay, I just want to, every problem I give you, please try to work it. If you work all those problems, understand all the problems, you should be good. Okay, I think the most important thing is you learn the knowledge. Heat transfer is an important topic, okay, for your undergraduate study here. Okay, so that's it for today. See you Friday, right? Today is Wednesday, so see you on Friday, 11, okay?